Assalamualaikum warahmatullahi ta'ala wabarakatuh and have a very good day. Today, I'm going to share with you how to design reinforced concrete pad footing with axial load and moment. Given here is the pad footing, okay, that is subjected to the axial load and also moment. Okay, this moment is come from the superstructure, especially from the nearby beam. Okay, so the axial force given here is the permanent action GK 720 kilonewton, variable action is QK 375 kilonewton, moment M 37.5 kilonewton meter, column size 300 millimeter times 300 millimeter, design life 50 years, exposure class XC1, material for the concrete is 35 Newton per millimeter squared, steel is 500 Newton per millimeter squared, unit weight of concrete 25 kilonewton per meter cube. Soil bearing capacity from the soil investigation is 150 kilonewton per meter square. Diameter bar is assumed as a 16 millimeter and the footing thickness is 450 millimeter. The first one that you have to do is you have to calculate the nominal cover. In order for you to calculate the nominal cover for the footing is same as what we have done in simply supported beam, but the difference is you only have to calculate the C minimum due to two conditions, which is due to the bond requirement and also the exposure class. Therefore, the C nominal is equal to the comparison between C minimum due to the bond requirement and exposure condition, which one is the maximum one. Therefore, in this case, the answer is 16 millimeter, then plus with the deviation 10 millimeter equal to 26 millimeter. Therefore, the nearest 5 is equal to, nearest biggest 5 is equal to 30 millimeter. Next process is determine the size of the footing. Okay, first of all, you have to understand this condition. In order for you to determine the size of your footing, is supposed to be not due to the factorized. Therefore, you have to calculate based on unfactorized loading. So in this case, the value given here is unfactorized for the GK and also QK 1095 kilonewton, which is the total GK and also QK. Then if you factorize the value is also different, 1.35 GK plus 1.5 QK. Then you have to calculate the footing self-weight based on the not factorized loading, which is 10% from your end, which is 109.5 kilonewton from 1095 kilonewton. Therefore, the area required is equal to the service load plus with the self-weight of the footing divided by soil bearing capacity. Therefore, the answer is 8.03 meters squared. So, what if the value given there, okay, is already factorized? Okay, it did not mention or it's not separate between the uh, permanent action and variable action. Therefore, for example, it gives the N is equal 1500 kilonewton, which means you have to divide this N value with 1.4. 1.4 is the average of the factor of safety, which is 1.35 plus 1.5 divided by 2 is almost 1.4. Okay, then to try the footing size for the axial load and moment condition foundation, you are allowed to provide a rectangular section of the footing. So that's why in my case here, I do provide B times H uh, is equal to 2.5 times 3.5. Okay, here is the thickness of your footing. Therefore, my area is 8.75 meters squared, which is B times H, is more than the required here. Then you have to calculate the new self-weight by calculating 2.5, which is the area, times 3.5, times 0.45, which is the volume of your footing, times with 25, which is the unit weight of your concrete, equal to 98 kilonewton. Okay, so means that it's okay, for you to have a lesser assumption of your substrate because we already get the exact size of the substrate. The early one is just a assumption of the substrate. Okay, Then you have to calculate the maximum soil pressure. The maximum soil pressure is equal to N, the service load, plus width W, which is the new surface of the footing, divided by the A, area of the footing, okay, plus with My plus over I. M is the moment given, 37.5, okay, time Y is 1.75. Y is equal to H over 2, which is 3.5 divided by 2. Then I is equal to Ixx, which is BH cubed over 12. Then you get the answer. Then you have to make sure that the answer of this maximum soil pressure, okay, should be less than the soil bearing capacity that is recorded based on the soil investigation. What happens if you get the condition of the maximum soil pressure is bigger than the soil bearing capacity? Then you have to change the size. Either normally you have to increase the size. When you increase the size, okay, you will reduce, okay, the total uh, value for this part. Therefore, it will reduce the maximum soil pressure. The next one is the analysis. The analysis is the process to determine the moment that is acting on the column or on the footing. So the moment that we have to calculate is the moment due to the longitudinal section and also transverse section. So here are the layout for the foundation. So here are the H, here are the B. Okay, the H is equal to 3.5 meter, and then here is 2.5 meter. Then the column size is 300 millimeter. That's why here is 1.1 meter and here is 1.6 meter, which is the LC. Okay, then you have to calculate the maximum and minimum of the soil pressure. So in order for you to calculate the soil pressure at ultimate load, P is equal to NED over A plus minus MY over I. So here are the calculation. NED is 1535, which is the factorized value, divided by area of the footing, okay, plus minus with the moment time with the Y over 8.93. 8.93 is the I. Then you get the P maximum and also P minimum. Okay, so the bending moment at the column face for the x-axis, okay, which is at this section, okay, at this section, is equal to 176 times 1.6 squared, which is, how do I get this 176? So by doing an interpolation at distance, okay, 1.9 meter, okay, from this, okay, you will get 176 kilonewton per meter squared of the soil pressure at this part, okay, at this column face, okay, and then divided by 2 plus 183 minus 176, 183 minus 176, okay, time with 1.6 over 2 times 1.6 over 2 third, because this is a trapezoidal, then you get the answer. Mx is equal to 5788231 kilonewton meter per meter. Then for the mxx, in order for you to calculate the moment, you have to time with the b, because the moment is acting perpendicular to the axis. So that's why you have to time with 2.5. And then for the MYY is equal to 175, which is the P minimum. 175, which is actually at this column face, okay, at this column face, okay, which is this value, NED over A is equal to 175, okay, time with 1.1, okay, LC for this one, okay, divided by 2, okay, and then you get 106 kilonewton meter per meter. And then you have to time with the 3.5 meter, because the moment is acting at the perpendicular section, which is for at the x-axis for the transverse section. Next process, you have to calculate the main reinforcement. In the main reinforcement, you have to provide the main reinforcement for both axes, which is longitudinal bar and also transverse bar. Therefore, as usual, the method that you are going to use is like a rectangular section of the beam, okay, or slab. Okay, so in order for you to calculate the first one, okay, you have to calculate the effective depth for both axes x and also y. So for the x is equal to h minus c nominal minus 0.5 diameter bar, and for dy is equal to h minus c nominal minus 1.5 diameter bar. For the longitudinal bar, the bending moment is mxx 578 kilonewton meter, and then you calculate the k, z, and also as here. Then you have to calculate the as minimum and as maximum here. Okay, so before I explain to you how to provide the reinforcement, I want you to understand about the as minimum and as maximum. So the AS maximum here is 0.26 FCPM BTD over FYK. BT is 2.5 meter, and then the D is 412, which is dx. Okay, and then you have to calculate 0.013 BD, and then you have to compare which one is the bigger, become your AS minimum. Then your AS maximum is 0.04 AC, okay, is equal to B times with the H. H is the thickness, not is the longitudinal length. Okay, then you get the maximum 45,000. Therefore, if you have a look, the range between the minimum and the maximum reinforcement area provided is quite big. Okay, why it is happen? Because we are allowed to provide the numbers of the reinforcement for foundation, which with large numbers. Okay, although the requirement is only 3395 millimeter, then we may provide bigger than this 12H20. If, for example, you would like to provide 20H20, it's okay because it will not given a justification, it will be over design of the section. Why? Because we would like to control the crack of the foundation. Okay, because the crack check, we have to check the spacing between the reinforcement by using a large numbers of the reinforcement. Therefore, we will reduce the spacing between the reinforcement, then we can control the crack check of the reinforcement and the structure will not fail. Okay, I will show the different what if I provide like this 12H20. In this case, either it will pass in terms of crack or not, then you will see the answer later. Then the same process that you have to do for the transverse reinforcement, and then you have to remember the B that you have to use is 3,500, same what you have done in your calculating of the moment. Okay, then the minimum and also maximum reinforcement, same as what we have done. Okay, as usual, when you design a footing, you have to do a shear check. The shear check process have to be fulfill the three main requirement, which is the vertical shear, and then the punching shear, and then the last one is maximum punching shear at the column perimeter. Okay, let's have a look on the first one. The first one is the shear. Vertical shear is critical at 1.0 D from the column face. Okay, so here is 1.0 D from the column face. Okay, so the moment, okay, the pressure here, okay, at the 1D from the column face is 180 by doing the interpolation. Okay, you have to do an interpolation. Therefore, here is the area of the vertical shear or the critical shear area of this foundation. Okay, and then the distance here is 1188. Okay, and then the first one, you have to calculate the average pressure at the critical section is equal to 168 plus 2.906 divided by 3.5, which is the length of this distance, time with the 15. 15 is the difference between 180, the maximum and minimum pressure here, 183 minus 168, then you get the answer here, 180 kilonewton per meter square, where it is the average pressure at the critical section here. Okay, and then vertical shear forces, VED is equal to 180 times 1.188, okay, time with 2.5, which is the distance of this part. Okay, 2.5. That is the formula. Okay, So it's equal to 535 kilonewton. And then you have to calculate the design shear resistance. The first one, you have to determine either we have to extend the bar beyond the critical section, because either we need to extend the reinforcement in order for us to cater this vertical shear or not. So we have to check this bar extension uh, at the critical section condition. If, let's say, the LC over 1D time minus C nominal is more than LBD plus D, okay, therefore no need for us to have the extension. Therefore, the allowable of the required area of the reinforcement is 0. So if we need, we have to provide the reinforcement based on the new calculation. Okay. So in this condition, we get the answer is, okay, more than the required. So means that no need for us to extend between the critical section. Then we provide the allowable area of the reinforcement is 0. So and then we have to calculate VRDC because the ASL here is 0. That's why we get here rho 1 is a 0. Therefore VRDC is ignored. Okay, should be ignored. Then we calculate the V minimum to compare, okay, or V minimum to compare with the VED, and then if it is more than VED, is then the answer is okay. Next one is the punching shear at the critical of 2D from the column face. The first one we have to calculate the average D is 412 plus 396, which is dx plus dy divided by 2. We get 404 millimeter. And then the 2D is 2 times with the average D, which is 808 millimeter. Then we draw this diagram in order for us to know the layout of the punching shear at the critical 2D from the column face. Then the control parameter is equal to 4 times with the dimension of the column. So let's say because this column have same size, therefore 4 times HC. For example, if they have a different size for each axis, then you should 2 times HC plus 2 times BC. Okay, so you should understand what does it mean. Plus 2 pi times 2D, and then you get the answer here, and then area within the parameter. Okay, so here are the formula AC plus 4HC, which uh, means that the perimeter, okay, perimeter of the column, okay, time with the 2D time plus with pi 2D squared, and then you get the answer. And then average punching shear for forces, okay, at the column parameter is equal to VED equal to 175, okay. 175 is from the previous pressure, okay, time with the area minus area of the footing minus with the area within the parameter, then you get 987 kilonewton. And then punching shear resistance, so you have to calculate the small VED, okay, which is the punching shear resistance is equal to beta times VED over UD, and then you have to calculate this beta by using this formula 1 plus K times MED over BEDU over W1. Then you have to calculate K. K is actually the coefficient dependent on the ratio between the column dimension C1 and C2. So C1 is the biggest dimension of the column, C2 is the smallest dimension of the column. So in my case here, so the answer is 1. That's why I choose 0.6. If you get in between, for example, 1.5, you may do an interpolation if you want, but sometimes we take a smaller value, then it's okay. Okay. So means that you have to choose one. Okay. So and then you have to calculate the W1, okay, which is 0.5 C1 squared plus C1 C2 plus 4 C2D plus 16D squared plus 2 pi D C1. Then you get the answer 3.99 times 10 power of 6. Then you have to calculate the beta. Beta is equal to substitute all those value that you already determined into this formula for beta, and then you get the beta is 1.03, and then you calculate the punching shear resistance here. Okay, then you get the answer is 0.41 Newton per millimeter square. Then you have to compare with punching shear resistance VRDC small and V minimum. And then the value of this one should be bigger than your VD, then the answer will be okay. Then the maximum punching shear at the column parameter, the first one you have to calculate the column parameter. So what is the column parameter? And then the punching shear resistance. a punching shear stress, which is VED, is equal to beta times with VED over U naught D. So beta, the same formula, the difference is only here U naught. Okay, so in W1 for this one, W1 for this one is equal to 0.5 C1 squared plus C1 C2. And then you get this answer, and then beta is you have to use substitute all those value in this formula. Then you get the answer 1.13. VED is equal to 3.56 Newton per millimeter square. Here you have to use a average D. And then V hard D max, then you get using this formula, and then you should get the answer is bigger than VED, then the answer will be okay. Then there are the crack check. On the crack check, what you have to do is the first one, you have to determine either the thickness of your foundation that you provide is okay or not. It should be more than 200 millimeter, because the 200 millimeter is the minimum dimension for your thickness. And then you have to calculate the steel stress equal to 0.6. This is the shortest method. 0.6 times with FYK over 1.15 time with AS required over AS provided, then you get 235 Newton per millimeter squared. Then you have to refer to the table. Okay, assume that the WK is 0.3 if not given. If it's given, you have to follow the value. By doing an interpolation, you get the answer for the allowable spacing between the reinforcement that you provide is 206 millimeter. Okay, then you have to calculate the actual spacing of the uh, reinforcement for both longitudinal and also transverse. Then the formula is B minus 2 C nominal minus diameter bar for both, and then over N minus 1. N is the numbers of the reinforcement that you provide. In my case here, okay, the B for longitudinal section is 2.5 meter, or 2,500 minus 2 times 30 minus 20 divided by 12 minus 1. Okay, and then the transverse is 3,500 minus 2 times 30 minus 16, okay, over 14 minus 1. Okay, and then 260. Therefore, both conditions showing that the structure or the foundation is failed due to the crack. What we have to do, okay, this is the things, it's back to the things that I do already share with you before, where we have to provide numbers of the reinforcement, largest numbers, so because it will affect the value here. Okay, so that's why we can have at least 15 or 20, so that we have to make sure that the actual here should be less than the allowable here. Okay, so this is the way how we going to provide the numbers of the reinforcement in order for us to control the crack check of the foundation. Okay, here are the detailing. So although the detailing is not follow the correct one, so I just would like to show the the position of the reinforcement for the footing. So I hope that by this sharing session, you really understand how to design the foundation due to the axial load and moment condition. So with that, thank you. Assalamualaikum warahmatullahi wabarakatuh, and have a very good day.